shear is my thick rope, so I'm going to draw it over here. So it's a really thick rope, and I hate thick ropes. You will see why I hate thick ropes. It has a length L, it has a mass M, and the whole thing is swung this way, let's say, with an angular speed of omega. And this part is the center, okay? And we need to calculate at somewhere over here, at a distance of 3L/4 from here, we need to calculate what the tension is going to be. Now, before I make you understand what's going on over here, let's look at a little bit different problem first. So, because we need some sort of a background, okay? And I'm gonna solve that first over here. And you will soon understand why I'm doing that. Let's take a completely different example. Let's say I have a 5 kilogram object connected to a 10 kilogram object connected to a 15 kilogram object. I'll promise you, you'll understand what the point is. And let's say the force with which I have to pull this whole thing, let that force be equal to 30 newtons. I want to calculate net force on this guy, and this guy. Let's quickly do this first, okay? Well, first, we understand it's a constrained motion. All the particles are gonna get the same acceleration. So I can treat this as one big object, right? So I can say F is equal to ma. So 30 equal to mass, that's the big object has a mass of 15 plus 15, 30 times A. So A is equal to 1 meters per second squared. All right, so we can now calculate the net force on each guy. Net force on this guy, so I'm gonna put the net force here. On this guy is ma, so that's going to be 5 newtons. Net force on this guy is going to be 10 newtons. Net force on this guy is going to be 15 newtons. And look at this force, this is 30 newtons. What I want you to realize is that whenever you have a string attaching a block of masses, the net pulling force, so the pulling force turns out to be equal to the sum, okay, the net pulling forces turns out to be equal to the summation of the net force on each block. Okay, do you see that? Is the so what I mean is here the net pulling force, the total pulling force, okay, is going to be equal to 5 plus 10 plus 15. So in general, we could say that if you had blocks attached this way, so you have a particle here, and a particle here, and a particle here, and a particle here, and so on and so forth, then if each one is getting a force of, let's say, F1, and this guy gets a net force F2, and this is F3, and a net force is F4. I know you have understood this, but I just want to make things clear so that we can solve our original problem clearly. Then the pulling force, the force that pulls this whole thing and accelerates this together, is going to be F1 plus F2 plus F3 plus F4. Okay? Is this concept clear? Hope this is clear. Let's now solve our original problem. Okay, what's that got to do with this? Everything. First of all, I want you to understand that the tension is not the same everywhere. The tension is going to change. And here's how I'm going to make you understand that. Look, let's divide this into lots of chunks. So let's say there's one chunk over here, that's another chunk over here, and so on and so forth. Look at this. Okay, the whole thing is L. I've divided into lots of chunks. Okay, first of all, look at this guy. This guy is pretty much at the center. His velocity is 0. So the required acceleration for this guy is also 0. However, if you notice for this guy, because it's close to it, but he has some velocity, some distance is there, and because of that he gets a small centripetal acceleration, so it requires a little bit of net force on this side. So the net force on this guy is a little bit big. So net force, I'm going to write down the net force on each one of them. I'm going to use purple for that. So net force for this guy is pretty much 0. The net force for this guy is a little big. Net force for this guy is a little bigger. The net force for this guy is a little bit bigger because he needs more acceleration. Net force for this guy is a little bigger. Net force for this guy is a little bigger. Net force for this guy is even a little bigger. Okay. Now look at the tension at this point. I'm going to use red for tension. Look at that, the pulling force here. the tension at this point has to be sum of all these forces. It's huge tension. The tension at this point, tension is always a pulling force, right? The tension at this point is the sum of these forces. It's not as huge though, as this much, so it's going to be a little bit smaller. The tension at this point is going to be a little bit smaller. Tension at this point is going to be a little bit smaller. Tension at this point is a little bit smaller. Tension at this point, smaller. Tension at this point, whew, huge, biggest tension. So you see how the tension is changing? Tension keeps changing as you move from here to here. Maximum tension, minimum tension. So what we need to find out is the net force on each guy and add all of them up. Or in other words, we need to integrate. So I hope I was able to qualitatively give you some idea of how the tension keeps changing and how the net force on each one keeps changing. The net force required is bigger. Of course, these are infinitesimal forces in reality, but you add up infinite amounts of infinitesimal forces and eventually they give you some macroscopic quantity. Okay? So our goal is to calculate what this net force is at any random distance and then add them all up. Okay? So let's do this correctly now. So I'm gonna go to some random distance x and I'm gonna calculate what the tension is in general. Okay? So let's say I go to some random distance x at this point, some random distance x, and I'm gonna break out one small chunk now. I'm gonna concentrate on that chunk, and that chunk has negligible thickness. That's dx, and the remaining chunk is over here, and that is our L minus x. That's the remaining chunk. Okay, we need to calculate force at this point. So I'm interested in calculating net force on this guy. Okay, so let's isolate that guy over here. This fellow is pulling him this way, so there's a pulling force this way. This fellow is also pulling him this way, there's a pulling force this way also. Okay, which force is going to be bigger? Quick guess. This one, because it needs an acceleration in this direction, right? So if this force is T, I'm just going to call this as T plus dt. That's the teeny tiny extra force you need over here. But T is the tension at this point, x. Okay? So if I calculate what dt is, I'm going to sum up dt all the way from here to here. Okay? And that's the amount of tension needed at this point. I hope you are able to understand it. I'm going to repeat. dt is the small net force that this guy needs. But to calculate this tension T, I will sum up all the forces of all the net forces from here all the way up to here. Exactly what I did earlier. Okay? Alright, so let's build an equation for dt. dt is the net force. So dt, the net force, has to be equal to mass times acceleration. That's the mass, small mass dm, times the acceleration. Acceleration is going to be centripetal acceleration. Centripetal acceleration is omega square r. So omega square into r is this guy, x. So dt turns out to be equal to dm. How do I calculate what dm is? This dm is the mass of this fellow. How do I figure that out? Well, we can just assume the density is a constant. So let me do that over here. We can say density, linear density, mass by length of the entire rope must be equal to linear density dm by dx. So dm turns out to be m divided by L times dx into omega squared x. Okay, so we now have the net force on this little fellow. But to calculate the tension, remember this is my tension. To calculate tension, I need to add up all the net forces. That's exactly what I told you over here. To calculate pulling force at this point, you need to add up all the forces over here. See? Okay, let's do it. So to add up, I have to integrate it. The net pulling force turns out to be equal to the integral. So I'm going to pull out all the constants. M by L omega square gets pulled out. I'm going to integrate now x dx, and we need to be careful. We're starting from x and we're going all the way to L. Yeah, that's what you're doing, right? So we're starting from x, from here somewhere, and we want to add up all the way to here. So to all the way till L, from x to L. Okay. All right. You know what we can do? We already know that we are supposed to start at 3L by 4, right? We already know that. We're supposed to calculate tension at 3L by 4. So let's just start from 3L by 4 and go all the way to L. I think that will make more sense. Okay. All right. So m by L omega square, and this is a pretty straightforward integration. It's x squared divided by 2. And then to apply the limits of 3L by 4 and then L. Therefore, the required tension at that point is going to be m by L omega squared into upper limit first. So you get L squared divided by 4 minus 9 L squared divided by 16. Okay, now all we need to do is a little bit more algebra. Let me start from here. Okay, so T equals m by L omega squared. Let's see, I multiply by 4, and oh gosh, there's a 2 here and there is no 4 here. What did I do? I'm substituting L, right? So I'm going to pull that 2 out, and L square minus 9L square by 16. Sorry about that. So I can't get negative answer. That's what I was thinking. So 16 minus 9 is 7. So 7 L squared divided by 16. So if you put it all together, T turns out to be, this L cancels, 7 m omega squared L divided by 16. That's what we wanted. Notice as you go farther and farther and farther and farther and farther away, there is less string to pull on. You don't need much pull. Correct? So because of that, tension keeps decreasing. Tension right at this point, as you can see, is very small. However, net force keeps increasing. Notice that the net force keeps increasing. That's what you need to understand. Net force on each mass, of course, all of them are infinitesimal forces, so I really have to put dFs everywhere. So let me just do that. These are all dFs, infinitesimal forces, but they keep increasing as you move along, and that's the part where we need to integrate. However, notice the tension keeps decreasing. Tension required because the chunk keeps decreasing. Alright, so I hope you were able to understand. So if you were to calculate tension here, it would be from L to L, and you would end up with 0. And that makes sense. And if you were to calculate tension over here, it would start from 0 to L. That would be the maximum, right? This chunk would go, this part would go over here. So the maximum tension would be at this point, and that would be m by L omega squared by 2 into L squared. Alright, so I hope you were able to get some insight and some intuition behind a massive rope problem.